Okay, in this one we are going to do a reflection of the figure over the line of reflection R. And the idea behind this one is we're going to use a construction for a perpendicular line through a point. So if we had the line here, for example, and we wanted to do a perpendicular line through it, we would use our compass, swing an arc, and then bisect the arc that was created. And in doing so, we would create perpendicular lines that pass through the given point. So like so. So we know that would be perpendicular. In our case, we're going to treat this as if it's our line of reflection and point on the figure, and we're going to extend that out just a little bit further so that we can do our actual reflection, because we need every point to go through the line of reflection at 90 degrees and then the same distance over on the other side. So first step is going to be to use our compass. We're going to put it on point B. Doesn't matter which point you do first, but point B is a good one to start on. And we're going to swing an arc that intersects our line of reflection in two different places. So it's key that it hits it twice. And you don't want it to be too close together, you don't want it to be too far apart. It's just kind of looking for that just right spot. If it ends up passing through a space where the line of reflection does not hit it, you can always extend your line of reflection. All right, from there, we want to bisect the segment. So if you take your compass and bisect the segment, so create that perpendicular bisector. That bisector will in fact pass through the point B and will also be perpendicular to our line of reflection. And we just extend that out so that when we do our reflection of point B, we have enough space. So we know this is perpendicular, and the final step is we want to double the distance of B to the line of reflection. So B to the line of reflection is our setting on our compass, and then we flip it over to the other side. So then we know the length of this segment is congruent to the length of B to the line of reflection, and this is our point B prime. Couple other things here, ideas that you might see or like. If you do the construction, so say for point C, if we do the construction, same one, and what we do instead of just bisecting the segment, if we keep our compass the same setting, if you go over to the point of intersection, it actually touches C, definition of a circle, the radius is the same, but if you now swing intersecting arcs with that same compass measure, so still touching C, what actually ends up happening is this ends up being the location of C prime. And the reason for that, you'll see it in our quadrilaterals unit, but what we've in fact done here is we've created a four-sided figure where all the sides are the same length. This is called a rhombus. And a key property of a rhombus is that the diagonals are perpendicular to each other and bisect each other. So that means that A, if we connect C to C prime, it's going to be perpendicular, and B, the diagonals bisect each other, so one diagonal cuts the other in half, so this half has got to be equal to this half, which means this is our point C prime. So it cuts a little bit of the construction out that you had to do on the other one. A couple of things you can do, which I don't really want to see in your videos because they do kind of sometimes end up with slight variations in what you want, but if you take your protractor and turn it so that the 90-degree line and the crosshair are both on your line of reflection, the back of your protractor is in fact now perpendicular because it runs parallel to that 0, 180 line. So like if I line it up here with my C point, I notice that, yep, I drew a perpendicular line. The problem being, I cannot reach the point A using this method, so I'm very limited based on the size of my protractor. Another one you can do, your set square has a built-in 90-degree angle, so if you lined up one side with the line of reflection and then slid it over, you would get pretty close to drawing a perfect 90-degree angle and then trying to extend it. problems being a lot of times we can have just little bits of human error there, so I don't really want to see that. What you can do, however, is once you have your first perpendicular line drawn, we can use the same method that we do in translations, which is to copy parallel lines. So the idea here is it's called the converse of our corresponding angle theorem, that it was when we created corresponding angles that were congruent, we ended up with parallel lines. Now what we're saying is if I draw a line parallel to B prime, it's going to be also perpendicular to the line of reflection. So if I now slide my set square up to A and draw in that line that is parallel to B prime, so we know that these two have to be parallel. Since they are parallel and cut by the same transversal, we can reason that the corresponding angles have to be congruent, and therefore our line drawn must also be perpendicular to the line of reflection, which is great because that's exactly what we need to do for reflection. We need that perpendicular angle. And then I'm just going to measure out the distance from the line of reflection to A and mark it on the other side. And notice I'm just a little bit short, so I put a little arc, and then I'm just going to extend that line I drew. And there is our point A prime. Final part, connect and shade. So there is our image. I should have drawn the point C prime outside of the figure, but no harm, it'll be fine. And just shade in your image so we can tell the difference between. You should notice that your original image, or your pre-image and your image, are congruent to one another. Their corresponding sides are the same length. And their corresponding angles are also the same. So we have produced a rigid motion in this case. We've produced congruent figures from transformations.